And our first speaker is Dr. Karriker. Dr. Karriker is a Morill professor focused on swine medicine in the Department of Veterinary Diagnostic and Production Animal Medicine, and is the inaugural holder of the Dr. Douglas and Ann Gustafson Professorship for Teaching Excellence in Veterinary Medicine. His position is a mix of teaching, professional practice, research, and university service activities focused on supporting the development of swine veterinarians and practitioners globally. Dr. Karriker is currently the director of the Swine Medicine Education Center, and this afternoon he's going to talk to us about Baloney detection, key characteristics of field trials you can trust. Welcome, Dr. Karriker.
Thank you. Well, thank you very much. Really appreciate the opportunity to address this group. A lot of colleagues and mentors in the audience, so no pressure for me, but it looks like we're not getting out of it, so let's get after it. My task is to talk about baloney detection because it's a swine meeting. If it was a beef meeting, it would be something more like BS detection, right? So you're picking up what I'm putting down. And really what I want to talk about is characteristics that would be important to consider when designing a field trial or when reading a report about a field trial and considering putting that information in. So I'll be talking from both of those perspectives at different times, and I'll just sort of leave it to you to kind of imagine what the opposite of that would be as we go along. So really, what characteristics add value to field research projects and increase confidence in the conclusions? That's really what we want to look for. So I'm going to go through three broad categories: important research elements, so in general, research procedures, techniques; practical ways to improve field trial success, so here's a lot of nuts and bolts mistakes I've made, frankly, that you should probably not repeat; mistakes in scientific thought, too, that kind of get in our way when we're trying to figure out how to do field trials and so forth. So, important research elements. The first is just to kind of refresh on the definition of a field trial, because I think we'll have a little different perspective on what it is. Potentially, you know, it's a trial that's undertaken on subjects in the field, obviously, that's under husbandry and management practices, typical of those under which the procedure is intended to be used for, or the intervention, right? So operational conditions. The trial is frequently prophylactic or preventive, therefore relies on natural challenge in a lot of cases. To the treatment that's being assessed. So assessment of the efficacy of a bacterial pneumonia vaccine, for instance, would rely on vaccinated animals being naturally exposed to infection with the relevant bacterium during the period of the trial, right? So that already introduces a little less control. But what's important is what's not in the definition. There's really nothing in those definitions that suggests that we should accept a lower level of quality or rigor or ignore best research practices just because we're out in the field, okay? We might intentionally swap an environment with greater control, like the laboratory, for an environment with more relevance to the real world, the field, where the results will be implemented, right? But that's a conscious trade-off that we're making. It isn't necessarily a situation where we want to neglect tried and true research rigor and procedures. All right, so the most important thing to get started, the most important element is the question, all right? So we often think about them in terms of PICOT questions. They're clinical research questions that use this mnemonic to help identify the core issues. The P is the patient or the population or the problem. I is the intervention. C is comparison or control. O is the outcome. Or the objective, and T is the time frame, okay? And so an example of how you tie all these things together would be the questionnaire at the bottom. In conventional nursery pigs with clinical streptococcus suis, that's the problem or the patient. What is the effect of oral amoxicillin at 5 milligrams per kilogram body weight? That's the intervention. Compared to no treatment, that's our comparison. On group mortality, that's our outcome or objective. At transfer to the finisher, that's the timeline, right? We're going to measure them through the nursery phase. If you don't have this question structured with most of these components, you should stop your field trial. it determines just about everything else down the road. It takes a little bit of discipline, but it's very different than we're going to acquire some product and we're going to try it and see what happens, right? So establish this question and figure out what these elements are, and that will tell you a lot about the rest of your design. It'll solve a lot of questions for you as you move forward. So we talk about significance a lot, and in field trials especially, there's statistical significance, which requires planning, hopefully allows the elimination of some non-treatment effects. So we're trying to get rid of variation. We're trying to get rid of characteristics of the group that might show up in our numbers but don't really reflect what we're testing. And subtle differences just generally require larger sample sizes. There's economic significance, right? And that's the driver of a lot of field trials. A lot of times we go to the field because we want to see what the value is in that setting. And so it's often set up to inform some sort of cost benefit about the treatment or the intervention, right? What's going to be the utility of this if we decide to implement it based on our trial results? So how do you get to significance, right? Ultimately, we got to take those criteria of significance and translate it into a sample size. And sometimes we don't have all the information we need to do a traditional statistical sample size calculation. So where do we start in terms of designing our trial? Well, what you can do is sort of reverse engineer it, right? So you can look at the intervention in the system and go, how much is it going to cost to implement that intervention? That's usually one piece of information that we do have. What's the vaccine going to cost? I know what my labor costs are. I can figure out what the total cost is going to be. Then I'll look at the parameters that it's likely to change. So in our simple case of the vaccine, it might be mortality. And I usually have data in most farms, most systems on how much mortality costs me. So now I can figure out, in order to cover the cost of the intervention, how much do I have to change mortality, okay? So I'm already on my way to figuring out several of the pieces we need for a true power calculation. The next thing I need to know is what's the variability in those mortality numbers, and we probably have that in a system where we have any history, right? We can look and see how those numbers jump around. And then last is plan a trial to provide statistically significant result at this level of significance, right? A bigger trial might detect a more subtle difference, but if we can't recoup the cost of our intervention, it's probably less important to us, honestly, if we're in the field. Okay, so then we take that information and we do a real power calculation, right? Power calculations are the statistical tool that we use in study design to evaluate the likelihood that a study of a given size will answer the question. That's really what we want to get to. We don't need any more or any less in our sample size than what will answer the question. So they're fairly simple online calculators that are available. Most of the time, you only need 3 pieces of information. You need to know the effect size. So that was our difference in mortality that would cover our cost. You need to know the variability, okay? So that's the variability in the data that we talked about that you can look at historic measurements and grab. And then you need to know the risk of a false positive that you're willing to accept. And that's just a number you establish as your risk in taking that study. Most of the time it's something like 5%. You know, I'd be willing to be wrong 5% of the time is essentially what you're choosing there. Why not be right all the time? Why not make that 1%? Because that drives your sample size up, okay? So there's a trade-off there in terms of cost. Okay, and the reality is a lot of our decisions are made with much lower level of significance, honestly, in the business world. So 95 is pretty good. We talk about validity too. So there's internal and external validity. So I alluded to this earlier in the definitions, right? Internal validity is things like quality control, data integrity, objectivity, blinding when we can do it. Those things that give you more confidence that the numbers you're measuring are a result of the intervention that you've applied. And then there's external validity. How much does it apply to other farms in the system? How much does that result matter to the system that I'm working in? What's the likelihood that I could reproduce it at other times, right? So seasonal reproducibility would be just one example, okay? And then the utility of the results, right? You have to ask these questions in a field trial. What's the ability to manage the intervention or treatment? Is it something that we can actually do in the system before we spend a lot of time figuring out its value. Can production personnel and processes, can they accommodate the change? Am I gonna have to give up something else that they're doing currently? You know, we rarely go to farms where the employees just have an extra hour and we got to figure out how to use it well. Usually they're doing something, so that something's going to go away, and that's part of your cost, right? Does the intervention conflict with company principles? Is it something that, you know, we have another reason to steer clear of, whether that's company values, production goals, qualities of the product, things like that? It may not be valuable to measure variables in a field trial that can't be actively managed, right? And so if you can't impact them, probably doesn't make sense to consider them as something that will move in your particular trial due to your intervention. All right, so there is a hierarchy of evidence, and this sort of lays the groundwork for a little bit of what we're going to talk about study design here in a minute. And this is probably more important from the perspective of I'm reading studies and I'm reading about trials and things like that. But in terms of clinical evidence, when we're looking for support to make decisions about treatments and so forth, we generally look at this hierarchy, right? And so at the very top is systematic reviews with appropriate meta-analysis. So these are studies where they took a whole bunch of research trials, pulled the data out, subjected it to additional statistical evaluation, and reached a conclusion that incorporates a whole bunch of trials, a whole bunch of repeatability. It's really strong evidence. It's very, very rare in the pig world. There usually aren't enough individual trials to meta-analyze, so we rarely have the benefit of this information. Below that then is blinded, controlled, randomized trials. This is what most people think of as a laboratory trial. I'm here to say you can do these in the field too. They're harder to do. You have to make some conscientious compromises sometimes, but it should still be what we're striving to. Then there are observational studies where we get studies started, assign the animals a treatment, and we watch what happens and collect that information. There are case series where they aren't necessarily trials of head-to-head comparisons, but there are several cases that are relevant. And so those cases all contribute information. And when you look at the series collectively of these case studies, you have a little more understanding of what happens in typical cases, right? Some diseases we can't replicate in the lab. We can't culture the causative agent. We can't challenge animals and create a challenge model. So we're dependent on analyzing these natural field cases in those situations. And if you don't have a series and you just have one report, that's slightly less strong evidence, right? But that's the next layer there. When you get away from that, then you get into things like consensus reports. So this is when you get a whole bunch of experts together and they bring their experiences together. Comparative animal research. So now we've taken one step lower. We're now in another species altogether, and we're extrapolating back to our species of interest. So you can see that there are starting to become some limitations to the value of that. In vitro, so bench top trials with less than the whole animal. So now we're sometimes those are the best we can do because we can't study it in a whole animal. But if we have evidence from multiple levels, we tend to go with the decisions that are made at the higher levels, right? But sometimes the best we can do is an in vitro study with part of an organ system or something. Then you get into substitution variables, okay? So we measure blood, for example, to estimate lung tissue. So most of my current research is in pharmacology. We seldom get much higher than number 9, honestly, when it comes to pharmacokinetics. It's hard to measure drug levels in tissues that we care about, so we measure it in blood, and we hope that that represents what's going on in the tissue. So we're already sort of have a ceiling sometimes in the information we can bring to bear. Then you get into computer models, and then you get stuck with what you have right now, which is expert opinion. So very, very low on the list, actually. And I've come to terms with it, so it's all good. So all those really, if you look at those trial designs and why they rank the way they do, it sort of comes down to 4 basic things, right? Systematic observations are more valuable than random observations, right? So we talked about up at the top is the meta-analysis. All the data is treated the same. It's harvested under the same conditions. It's very systematic, okay? Random observations are what you get in case reports. Whatever struck that person to report about that case is what they reported. It might not be very systematic at all. Less bias, or at least knowing what the bias is more valuable than unknown or high bias. Okay, so It's almost impossible to do a field trial without some element of bias, okay? As long as we know what it is, we can judge the results accordingly. It's when we don't know what the biases are that become a challenge. Detailed and complete recording is much more valuable than conclusions alone. So when you're reading a paper, I think you always have to ask yourself, why did they not explain how they collected the tissue or how it was processed? I think it's valid to wonder about that. And so you really want to see that detailed, complete reporting. And then similar systems are more valuable than research done in systems that are unrelated. So, you know, again, working with the pig provides more useful data for pig decisions than working in another species, right? Okay, got to use statistics. This is one part that everybody hates about field trials, it seems like, except for 2 or 3 people I know, and that's partly why I know them, because I get them to help me with my statistics. So find a good statistician, somebody who gets a little geeked up about it, and that'll really make your field trial experience go better. Use statistics, but don't be a slave to an arbitrary p-value, right? Hear a lot about, well, it didn't hit p equals 0.05, or it wasn't less than p, less than 0.05, and therefore it's not significant. That's not exactly true. There's not much difference between 0.04, 0.05, and 0.06, right? They're all very, very close. And the reality is we can measure biologically or economically insignificant differences that achieve statistical significance when you have a big enough sample size. So you measure enough animals, you'll find a difference that turns out to be, as we call it in our group, a difference without distinction, right? So it's much more valuable to state the actual p-value. Let's call it what it is, get an idea of exactly where the trial landed in terms of its statistical power and the likelihood that it occurred by chance, okay? Not whether it just crossed some arbitrary threshold. So do it when you conduct the study, look for it when you read the studies. All right, statistics can be simplified. This is probably the most valuable thing that I've read in a while, to be quite honest. It's a series that ran in the Journal of the American Veterinary Medical Association for almost a year, January to October. And really, they took and tackled various parts of trial work, research trial work, from describing data to conducting various statistical tests and so forth. They're short reads, they're 3 or 4 pages. They simplify it, but not to the point of being incorrect. So it's an incredible resource. If you can't get access to it, let me know and see what we can do. This is one of the examples of something they have in there that I still reference now. And so this is a decision tree on trying to figure out which statistical test to use. And I like decision trees anyway, so I was automatically attracted to this. But, if you don't have any sense or data, you're comparing 2 groups with respect to the means or distributions. If they're paired, you go this way. If they have a normal distribution for the differences, now you're here. Boom, you're going to do a paired t-test, right? And after this point, usually there's a software package that'll take over for you. So it helps get you in the right spot for most tests, right? There are subtle cases that don't fit the tree well, but they're awfully few and far between. Experimental units power the study, okay? And the experimental unit, these 2 things are confused a lot. The experimental unit is the unit to which the treatment is applied. So it's the smallest unit that could receive any of the potential treatments. The observational unit is the unit on which the response is measured, right? So an observational, if you think about applying something to a barn, we're gonna run a feed additive into a pair of finisher barns. The whole barn gets treated. That's the experimental unit. It's that barn. You have 2 barns, you have 2 experimental units, right? Now, you might weigh 1,000 pigs in each one of those barns. So the pig might be the observational unit. That'll get rolled up to represent the barn, but your statistics are all driven by the experimental unit, okay? So kind of walking through that in your head and getting that squared away is really important for figuring out what your statistical package will look like. All right, we should randomize treatment assignments to experimental units when we can. We can't always do that in the field. Sometimes it's very difficult, but it helps us to avoid bias again. So hopefully if there's anything that affects our measurements, when we distribute things randomly, we distribute it evenly. That's the hope, so that it doesn't affect our outcome. Hopefully makes groups comparable then. probably increases the probability that our observed differences are due to the treatment and not some unknown factor. And so how do you check for random assignment or treatment, right? I had a healthy argument earlier this week with someone about how treatments were assigned, and they said it was random, and I disagreed, and I don't think either one of us convinced the other, but still, they're healthy discussions to have. And I think part of it is if assignment of the treatment to anybody in the study affects the assignment of other members in the study, it's probably not that random, okay? It's not an absolute rule, but it's a good starting point. So if I apply treatments, 4 treatments, 1, 2, 3, 4, and I just apply them to pigs in order as I pick up the pigs, that's probably not technically random, right? So just sort of an easier check to try to get there. And then if you have, you run into challenges with that, we can help you out. You should blind or mask when you can. Again, not always easy to do. But the whole point of blinded studies is so that the person making the evaluation doesn't know what treatment the animal it's evaluating got, okay? So you can imagine immediately this is much more important for subjective things. If I'm looking at a pig and I'm giving it a scale for lethargy, right? I'm gonna rate its lethargy. Then if I know the treatment, it's might be a little harder for that subjective measurement to be unbiased, right? However, if I'm going to put that pig on a scale that I have calibrated, and I'm going to read that number off, it's probably harder for me to bias that, right, if I know the treatment. So masking is important, but it's not an absolute, and it depends on your trial situation. Anytime, though, you can split up the administration of the treatments with knowledge of the treatments and evaluating the data from the animals, you are adding opportunities to remove bias to your study. So when you can do it, it can be very useful. And you should use positive and negative controls, right? Often we don't do this, and it makes it very difficult to measure the effect. It also, in some cases, makes it difficult to know if your trial performed appropriately or not. So positive controls will often be in challenge studies, animals that are challenged with no treatment at all, and you'll have a group of animals that gets neither treatment nor challenge, right? You can imagine in field studies where we don't always challenge animals that it's a little harder to establish these positive and negative controls. But if you can, it'll add strength to your study without changing your statistical or changing your group size very much. And you should always plan your statistical analysis before collecting the data. There's 2 reasons for that. One is it really informs how to collect the data, what data to collect. It answers a number of planning questions for you, but it also prevents getting done with the fun part of the field trial and getting back to the office and staring down that statistical analysis and really looking for other ways to procrastinate, right? So get the stats part out of the way from the very beginning, and everybody knows what they're shooting for. All right, so now some practical ways to improve field trial success. That was the theory and some of the key components there. And so what are some practical ways? And a lot of these are things that I just learned by making mistakes and occasionally watching the mistakes of others, but it's really just no substitute for learning from your own mistakes, right? Once is a mistake, twice is poor management. So if you do nothing but limit repeating mistakes, you get farther ahead faster. So we actually used to keep a manual of that, a notebook, and before every study, my research group, we'd sit down and go through the book. It was excruciatingly painful. You don't like to relive all your mistakes, but we rarely, if ever, made them twice. And so that was helpful to us. Now it's all sort of digitized and whatnot, but keeping that and going through it occasionally is a good reminder. Important to have a single organizer or owner and choose them carefully. They have to have organizational and communication skills, understanding of daily production activities, adaptability, tenacity, but they don't have to be a topic expert, okay? They need to be the ones that are moving people and moving pieces, but they don't have to be the topic expert. And sometimes it's better if they're not, frankly. Then they can tap a topic expert to wax poetic on their topic and provide what they need, but ultimately they're driving the study. Often you have to find some source of funding, right? So it could be internally funded in a company. You likely have to cost justify while you're doing a study. Here we deal with things like sometimes we have intramural funding from organizations, extramural funding, pork producers, professional associations, things like that. And often they're going to issue a request for proposals. The thing that helped me the most on this front was when I was told to quit thinking about winning a grant and think about it as something other than a grant. What it really is a prepayment for a service or a deliverable. The best idea doesn't always get funded, right? You can have a fantastic idea, but maybe it's just not in line with what they want to fund, or you didn't convince them that you could bring your idea to fruition, right? Good idea is a prerequisite, so it has to be reasonably good, and you got to convince the grantor that you can accomplish their goal, right? So start thinking about it in terms of their goal, not your own research goal necessarily. And details about the process are critical. More detail generally increases confidence. Don't overpromise, right? That's a tendency, I think, for all of us a little bit. So don't overpromise and then not deliver. So let's assume we had an RFP that looked like this. Feline Foundation soliciting proposals for innovative approaches for capturing a common brown mouse. It's got to be user-friendly. It's got to be safe. Operator safety is critical. What I would do in this case is I would go through and highlight all those components that they list. I would then stick them in this list, and then I would compare it to my idea, right? So they want an innovative new approach. I'm going nuclear, so that's innovative, right? The common brown mouse, do I know what a common brown mouse is? Turns out they're brown, four toes. They're usually cellar dwellers, not attic dwellers. Got that one. A multidisciplinary team. Here's the folks I'm working with. It's got to be user-friendly. I didn't check that box. Consumer product, can we keep the cost low? How detailed is the owner's manual going to have to be to get the nuclear reaction right? Is it going to it needs to greatly reduce mouse populations. I know I'm going to be able to check for that because I'm going to compare sightings before and after, count new droppings, so on. So I'm going to do a chi-squared test because I already planned my statistics. Operator safety, probably not. And I'm way over budget, right? So, literally stack these things down and see how many boxes your idea checks before you fire it off. And a lot of times there's opportunities for improvement. Know your trial design, right? We talked about the hierarchy of trial designs and whatnot, but in another way, know what a day in the life of a sample is, right? Map the complex treatments. So here's a situation where we were training students and we had to consider the safety of the animals they were working on. So there's several decision points, right? If they could identify the correct location to collect blood, then we would move forward. If they could proceed with the sample collection and were successful, then we could move forward. And so map these things out so everybody's on the same page. And it might be blood samples. Who collects them? Where do they go in transport? When do they get to the lab? It might be a series of treatments on what days the vaccinations occur compared to data collection, right? But map it out so that everybody's clear on when things happen, and so your reader or the people that are going to evaluate your work can follow along and know exactly what happened when. Do a dry run. We do this before a lot of our studies, almost all of them. We sit down and we literally talk about, all right, so we got to the farm. How did we get to the farm? Who had the van? Who got the van? We're at the farm. We got a snare. Who brought the snares? Does the farm have snares? I don't know if they have snares. Literally sort of talking through that stuff. You find a whole bunch of holes in your field trial before you get started, and you get those corrected, and you move on a lot quicker. Use digital images to record information, transfer information, and back it up. So we use Box a lot here at Iowa State. You can put it on your phone. You have one button to press. It takes a photo and drops it in a folder. You don't ever have to worry about where it is when you want to look at it later on. Data loss happens. Sometimes it's pretty severe when it does. So you want to make sure that you don't run that risk. You also want to design a trial to minimize disruption of farm routines and limit dependence on staff. If data is worth collecting, bring additional personnel to the site rather than adding to the employee burden, right? They may not be interested in the trial. They may not necessarily be motivated to conduct the trial or answer the question at the level you are. So if it's important enough to do it, then it might be important enough to bring some help for the trial. I remember when I was in practice, talked with our research farm manager, and he was like, if I stack up all the things that are only going to take me 10 more minutes, he said, I'm working 22 hours. So, it seems little to you, but they got a lot going on. But communicate the protocol directly to the site managers and employees. Even if they're not going to be involved, tell them what you're doing, why you're doing it, so they're not wondering, and loop them in on the results. Give them some value for being, at least being present and being around. Bring waste containers, haul it in, treat it like the Boy Scout motto, leave it better than you found it. That's how you get invited back to do research. Have coolers and ice packs for transportation of biological supplies. And in the winter in Iowa, have some way to keep them from freezing too is sometimes an issue. We've run into that before. Coming from the south, that was a steep learning curve. Standardized sample methods and observations, right? Especially if you're gonna have multiple people doing it. So some ways you can do that is like build keys for the data you want. So in this case, we're sampling joints. And so we pulled together these 4 pictures that all sort of illustrated how you could access that joint. There's 4 different combinations of starting point, needle angle, and needle depth, all of which work for that particular joint. So we use that to teach the folks that were involved in the trial, and also occasionally to reference ourselves. You do 50 of these in a day, you can drift yourself, even if you know it really well. So it's kind of good for a mental reset. Here's one we did for fecal consistency. So we went from, well, it's kind of banana pudding and a little bit chunky, to it's yellow and semi-liquid, right? And so then when we had data that was consistent among all the observers, it was much easier to analyze statistically, much easier to know what was going on. And your first pass at this might not be right. We originally didn't have as many colors on here, and then we got pushbacks like, hey, the color I'm seeing is not on your chart. So some of these will evolve as you go. ID all the equipment that you bring to the site, especially tools, even if you're going to leave it. Maybe it says thank you to the farm if you leave the equipment with them at the end and you don't haul it somewhere else. But it's helpful for them to know that came from the trial. We always try to pre-label or use stickers rather than writing, because especially when you're doing work that's physically demanding, handwriting gets bad towards the end of the day. And there's nothing worse than a half a day waste of time to figure out if that was a 9 or a 6 or a 7 or a 1 and that sort of thing. And then you've interjected some lack of confidence in your data at that point. If you're going to print forms, make sure they're big and spacious forms, plenty of places to write easily what you want when you're in a barn setting. Anticipate a wet, dirty, humid environment and waterproof those data sheets and electronics. Whether you think it's going to get wet or not, it's going to get wet in a pig barn. Always have extra supplies, especially if the trial runs over the weekend, and anticipate that you're going to go through decon procedures on sow farms and some high health grow finish sites too. So will your research supplies survive the decon? You might have to change equipment, you might have to use different materials as part of that process. Have emergency supplies. So is gas for a small backup generator on a site that just couldn't seem to keep the lights on when we were doing a longer trial. So things like that. Make your IDs obvious, so avoid low contrast color combinations. Size of the tag matters. It's easier to find it if it's bigger with high contrast, and that might not seem important when those tags are fresh, but after 7 or 8 weeks in the barn, it's amazing what they can obscure. And then occasionally we'll do things like we use the tags when we're putting them with the lesions and photographing it. So those tags can go farther than just identifying a pig, and it keeps your data very tight and very secure. Make recording observations convenient, right? Keep the recording where you're doing the task, right? So here's feed recording notebook, and there's the feed scoop. And while we're talking about that, if you're using a feed scoop to measure, make sure it's calibrated, right? So here you can see that when it's empty, it's not registering correctly, and here's a screw to fix that. So make sure all your measurements are calibrated. Facilitate continuous communication, so ongoing notes about things. Imagine if something happened and you didn't come back tomorrow, then is everybody going to be able to carry on with the process as part of the trial? Take relevant measures. If you want to know the temperature of that animal, try to get a temperature measurement near the animal. Also pay attention to lighting, right? Pictures look very different up here at the top, whether the lighting is correct or not. This is actually just 2 different times a day. Still in the daytime, but you pick up a lot of other details, so pay attention to that, especially when you're using digital photographs. And then, be prepared for the weather. This was the forecast. This was what happened. So, in parts of the world, this is more important than others. All right, last thing, and I got to finish up and get out of the way here. So just a couple of mistakes in scientific thought that get in the way. The theory will influence your observations, right? If you believe myco will lead to sick pigs with pneumonia, you look for coughing pigs. You might want to make allowances for other effects, right? What if there's subclinical effects? The observer changes the observed. So your presence, a new individual on the farm, might change the way people behave and do things. You need to make allowances for that. Equipment can construct results. So this was a favorite of mine. The temperature sensor is right in this pathway from the heater. Heater comes on, temperature warms up. This shuts the heater off, turns on the fans. That cools it off. The whole cycle repeats. Temperature in a barn looked like a roller coaster. Anecdotes don't make science, right? They gave us some free product to try. We ran it in a few barns. Those turns had better performance than the previous turns. That's an anecdote. It's useful as a guiding point, but that's not a rigorous evaluation. So pay attention to those things. Bold statements don't make claims true, right? So surveys say 11 of 12 Nobel Prize winners use bubblegum gum because it freshens breath the best. Actually, 2 mooched it off their grad students, and it's important to note there's no Nobel Prize for personal hygiene, so it's totally irrelevant. It sounds sciencey, but totally irrelevant. And popularity does not equal reality. Even if 150 people have the same bad idea, it's still a bad idea. This is a polar plunge, so now you know what I think about those. Representatives, a tendency to remember hits, ignore the misses. So if your friend calls right when you're thinking of them, is it ESP? I mean, how many times did they call you weren't thinking about them? You don't remember those because it didn't strike you as unusual or interesting at the time. Hasty generalization, right? So often we will extrapolate a decision to 4,800 sows based on the results of a 6-sow trial. We do that for a whole lot of our pharmacology stuff. So it's an area we need to work on. Over-reliance on authorities, right? The internet's the new authority in this age. Testimonials, all vets are equally capable of working on cats. It would be malpractice for me to work on a cat now after years in swine. So in God we trust, and everybody else brings data. And then sort of either or, right? The thought that if you discredit one position, then the opposite position must be true or accepted. And that dichotomizes the world in only 2 options, which really isn't true. And the example we see is, the FDA has not banned certain nutraceuticals or analogs, so they got to be safe, right? The reality is the FDA just hasn't evaluated them, so they don't have a status really in that respect. There's a third option. And then wrapping up here, the Planck problem, ideological immunity. This is important. A lot of people doing research are very smart people with high IQs, and they have a great ability to defend a position or an ideology. But the problem is that means they also have a very poor ability to embrace new ideas or change their paradigms, right? So that's important for you to think about as you're doing a study. It's also important for how you communicate a study. It's going to take strong evidence to convince smart people of new things. Lastly, communicate with repeatability and continuity as the standards. Your trial report should have enough data in them that somebody else could repeat it and prove it. And peer review, as I tell my students, is not a self-esteem building process. So embrace the criticism, take it for what it's worth, put it in your book, and don't repeat the mistakes. So thank you very much.
We have time for a couple of questions for Dr. Karriker.
So when we look at the standard convention for the p-values is the 0.05. And if I had to be 0.05 right all the time, I wouldn't do very much. And so I think sometimes we fall into that trap of, well, it's the same because the p-value was 0.05. You talked a little bit about the sample size, but there's some other things too that can affect that, right?
Yeah, that's exactly right. And so, you know, a lot of things that you said there really. I think the important thing, it really goes back to knowing what is the p-value for that particular result, right? That gives you an estimate of how likely that result just happened randomly by chance. That's really what ultimately you're getting out of that value, is some feeling for that. And, you know, in business, a lot of decisions are made on a maybe not much better than a coin toss, right? That's a P of 0.5. So, you know, to get 10 orders, you get an order of magnitude better comfort that the change is real, is meaningful. That's important work, right? So yeah, I think, you know, there are a lot of p-values that could be relevant. Now, you know, a lot of times what we're doing there is we're establishing that a priori, and that's when it makes sense to go, for our purposes, we're gonna say if the p-value is not less than 0.05, that these two things are the same, right? And you're establishing that ahead of time. But as you read the study and you go, well, that might not be quite that rigorous for my purposes. If they report the actual p-value and it's 0.08, you go, I'm comfortable with 0.08, right? So that's why I think it's important just to report the actuals and not an arbitrary one. But yeah, and I think that's the danger of just reading the conclusions, just reading the abstract and the conclusions. Because if they go, there was no difference, is it because they used that cutoff, or is it because they had a p-value of, you know, 0.9 or something? So, yeah, really good points there.
Any other questions for Dr. Karriker? If not, let's thank Dr. Karriker once more.